So, has anybody here used microemulsions or have some experience with them, or you've used them but didn't know why you were using them?
How about taking a workshop from Professor Baglioni?
When was your workshop, Chris, when you did that with him?
Maybe 3 years ago now at Pratt Institute in Brooklyn.
So it was what? So 2017 or 18?
Oh, I'd have to look it up.
Hmm. Well, it's kind of funny because between 2018 and 2020, I feel like that whole group kind of hit their stride and they were just pumping out papers. And there was a new analytical technique that, well, it was new to them in their lab. And the quality of their work really jumped up in 2018. So it might have been just like right after you took that workshop with them because they were still using the sodium lauryl sulfate with co-surfactant, right?
He didn't really say.
Oh, okay. I wonder if
Yeah.
they were using the new surfactant at that point then with a co-surfactant. I'm not sure.
Someone is saying that they used them after a workshop with Brownwing or Ormsby, and it was the same in my case. She came to the Hamilton Carr Institute in Cambridge to explain about microemulsions, nanogels, PEGI gels, and so on. So she's touring around UK as well.
Very cool.
Hmm.
That's great. That Rothko project that they did at the Tate was just phenomenal, and I was blown away by the analysis that they were able to do on the soil and how they were able to design a solvent system for that. And what was really kind of incredible is I was actually able to use the modular cleaning program to kind of reverse engineer how they got there. And so I was able to basically design what that graffiti pen was and put it into the MCP and then design a solvent system that would remove it. And it was the exact same solvent system that they found removed it. It was really cool.
That's very, very cool.
Since it's all based off of the Hansen solubility parameters. So we've got some people who have used them. That's really cool. Well, hopefully you can all learn a little bit more about them today. We go pretty deep into surfactant chemistry in this one. We kind of take the gloves off and go for it. So I'll hand it over to Jenny if we maybe want to get the video going.
Stop sharing my screen.
Is everybody still awake?
See, I haven't been able to check the chat because obviously, if not, you will all see it, how I hover around the screen. And
let's see. So I've got a couple of the questions recorded over here. The first one that I saw asked, in order to make a microemulsion, what's the minimum amount of surfactant you need to use? Up to 40%? Question mark. So when working with surfactants in general, you want to work with the critical micelle concentration, which is based on the molarity. So it's about how many molecules are in your solution per liter, as opposed to a percent, like a percent weight or a percent volume or something like that. That said, you generally want to work with between 1 times the critical micelle concentration to 10 times the critical micelle concentration. With something like EcoSurf, I just made a big deal about CMC. What that comes out to for 10 times the CMC is about 1 weight percent. So they're kind of related, they're kind of not, but most of these surfactants, they're generally around 1 weight percent for some of these non-ionics that are in this class of ethoxylates that we use. So you can get a cleaning effect for dewetting with as little as 2 times the critical micelle concentration. For detergency, if you're using it to clean a surface, say a very soiled surface, you probably still want to be up around that 10 times the critical micelle concentration. I actually don't really think it's that much more difficult to clear 10 times CMC as opposed to 5 times CMC. I don't think you would really honestly be able to notice something like that. So I don't think there's any harm working at that cap of 10 times.
Just let me add that for the water and oil emulsions, the ones we have so far from the CAPS cleaning acrylic paint surfaces workshops, yes, we do go up to 30%, 20%. Some of them even go up to 70% surfactant. And that's something we really need to kind of reformulate and come up with better inverted phase microemulsions. Remember, Luke's been talking about water-based microemulsions, where the continuous phase is water.
Right, we're being very careful to stay away from the water and oil microemulsions. So that's water inside of a solvent, that's the bulk phase, because of the extremely high amounts of surfactants that are required in the recipes that have been published. I think that we can do a lot better than that, and I think that we can probably, by the end of this year, have some really good water and oil microemulsions ready to go. So I hope that answered the question. It's a long answer. It's 1 to 10 times CMC. That's the long and short of it. If you're using EcoSurf, it's 1 weight percent. So the second one was a really cool question asking if there's a range in cloud point temperature before phase separation occurs, and is it different for every surfactant? So yes, there is a range in cloud point temperature before phase separation occurs. It depends on what's in your solution. So if you're talking about one specific surfactant, the cloud point temperature changes according to what's in the solution. So if you have 5% of a solvent in a solution, the cloud point temperature will be different than if you have the same thing, but with 20% of that solvent in there. So as you add more of that hydrogen bond accepting solvent, like the MEK, like the propylene carbonate, the cloud point temperature of the solution becomes lower. So the cloud point gets closer to room temperature, which is why the cleaning, why the efficacy increases. So there is a range, and it is different for every single surfactant. Each surfactant has its own cloud point temperature that's determined by its composition. A lot of these that are this class of non-ionic surfactant that are the polyoxyethylene fatty alcohol surfactants like EcoSurf, Surfonic, those kinds of things. Those tend to have cloud point temperatures between 40 to 70 Celsius or something like that, depending on the structure, and it changes for each one. But that's kind of a general area where they are.
There was another question about hydrophilic lipophilic balance in relation to the cloud point. I think some people missed the surfactant, the previous session.
Oh, well, that's okay. So that's actually another really good question. I don't know if we've covered that before. So the HLB and the cloud point are intimately related. The HLB is determined by the ratio of the polar head group, the size of the chain of the polar head groups. So if there are 10 polyoxyethylene units at the end of a chain, it will have a different HLB and cloud point as if it was that same molecule, but with 15 of those groups at the end, if that makes sense. So the more polar the molecule is, generally the higher the HLB will be. And the higher the HLB is, generally the higher the cloud point temperature is. So why is that? It's because it's a more polar molecule, so you have more hydrogen bonding, so the molecules stay stuck together better, so the cloud point temperature is higher, if that makes sense. So they're bound more strongly through hydrogen bonds. If you have a lower HLB, that means you have less polar head groups in there and a larger lipophilic tail. So that's your carbon chain when we talk about the lipophilic tail. So that means you have more van der Waals interactions as opposed to hydrogen bond interactions. And a hydrogen bond is 10 times stronger than a van der Waals interaction type bond. You guys might learn them as London dispersion forces and things like that. But van der Waals interactions are about 1/10 of the strength as the interaction of a hydrogen bond. So that's why if you have a molecule that's more polar, it's bound more tightly, it's bound more strongly, its Cobb point goes up, and its HLB goes up. One of the surfactants that I mentioned at the beginning, the Triton CG110, the alpha glucoside, that's based on a sugar molecule, and a sugar molecule is very polar. There are a lot of hydroxyl groups, OH groups on that, and that particular surfactant, CMC, is over 100 degrees Celsius, so it's above boiling, and it's because it's such a polar molecule. And it also has to do with the total size and other stuff like that, but that's generally what determines that. Someone asked, what is the nano in nanostructure fluids, the size of the droplets? So yeah, you answered your own question there. So yeah, it's generally the size of the droplets. You want them to be nano-sized, preferably below 100 nanometers in diameter. Some people define that differently. Some people define it as less than 300 nanometers, and I really don't think it matters that much. You can define it how you'd like. But somewhere between 0 and 300 nanometers, I would say, is a nanostructured fluid. What's important about a nanostructured fluid is really the structured part. Micellar solutions with surfactants, those are self-assembling molecules. So you put them in the solution and they go to interfaces by themselves. You don't have to do anything. That's why they're called self-assembling. So that's kind of the structured part. They assemble themselves into these structures and at interfaces. And so they're just doing that when they form micelles, they're doing it in small droplets. And that's kind of the long and short of a nanostructured fluid. But other nanostructured fluids, it's just kind of a general name. So you also have the swollen oil and water micellar solutions are also considered nanostructured fluids. Many emulsions are nanostructured fluids. Oil and water in oil emulsions are nanostructured fluids. So they're just kind of this broad class that generally have to do with surfactants.
There's another question here. It says, for dewetting, is it required that the microemulsion applied on the surface for a longer contact time?
Chris, I'll let you take this one because you've done it in a quicker amount of time than I generally do it.
Yeah, I've seen it happen in a matter of minutes. Like, it doesn't happen like working with wet solvents where it just rolls up right away with dissolution. But I've had it happen in a minute, even sometimes a little bit less. Luke mentioned the idea of putting out a layer of B72 on something and playing with the dewetting solvents. In the workshop I did with Professor Baglioni, there was a sample painting that had been varnished with B72 in another workshop at Pratt Institute, and we used one of the microemulsion systems of the pre-mixed microemulsions that Baglioni's group sells. And we were able to put it on with a poultice for, I think it was about a minute, and remove the poultice and then mechanically push the B72 off a natural resin varnish and grime layer without disrupting the varnish, the oxidized varnish or the grime layer. It was quite astounding.
Yeah, for me, it generally takes longer because I tend to work on wooden artifacts. So I'm working on wood as the substrate, whereas, a lot of other folks are generally doing this with paintings. So, a paint layer, which is very complex, is also very different chemically than wood. So that's part of the difference. The other difference is that generally when I'm removing coatings like this, they're like some of the most difficult coatings that exist if I'm doing this. And a lot of the times I'm working on either artifacts that have a coating that is so strongly cross-linked that they generally have to be removed purely by scraping or sanding, and they can't be chemically removed. So I de-wet those surfaces, and so it takes longer. Or I work on things that are often sacred artifacts. I'm here in Arizona in the Southwest of the United States. So we have a lot of tribal artifacts in our collections. And so a lot of those materials are 2,000 to 3,000 years old and extremely fragile. And so when I make micellar solutions for things like that, I'm very cautious with the amounts of surfactant and solvent I'm using. So if I use less solvent and surfactant, that also brings up the dwell time. So it has to sit on the surface longer, but then I do have less issues with clearance on some of those types of artifacts.
It says here as well, does dewetting occur in the same way with Pickering emulsions or self-polymeric emulsifiers?
It depends on what's in your solution. If there's a surfactant in the Pickering emulsion or in the polymeric emulsifier, it can definitely occur, and I've actually done that with a Pickering emulsion. That basket fragment that you saw earlier was actually a microemulsion loaded into a Pickering style emulsion, basically. So Pickering is kind of weird. So you're talking about charged particles. They're usually like a kaolin type particle. So I loaded the microemulsion into a kaolin type particle system and applied that to the surface, and that is what dewetted that shellac surface. You can load them into a lot of different things. I haven't done it with a polymeric emulsifier. Chris, you might have a better idea of this. I I don't know how that would work. I have a feeling it wouldn't work well because the solution would be kind of contained inside like the packets of the
Right, I
polymer
agree.
structure.
You don't have the surfactant to make that coating around the dispersed phase. So I think it probably wouldn't. You might be able to use carbopol as the gelling agent on a microemulsion system, but then that's not that's just a gelling agent, not a polymeric emulsion stabilizer.
Yeah. And when I think of Pickering emulsions, it's kind of like using methyl cellulose or something for an application like this. So you could just as easily use methyl cellulose as you would a Pickering emulsion or a Pickering type emulsifier, which are those charged particles. Methyl cellulose would work just as well.
She added now, I mean, if you don't use surfactants in the KSG 350 set.
Right.
Oh,
Oh,
okay.
go ahead, Chris.
No, you go ahead. Sorry, I just misunderstood the question. So go ahead, Luke.
Yeah, so if you don't have a surfactant, and it doesn't matter what system you're using, dewetting is not going to occur. You have to have it. The only other way to induce dewetting is to bring the temperature of the polymer that you're trying to remove above its glass transition temperature, which would generally set the object on fire. So that's the only other way to do it.
There's another question. What gels are compatible with microemulsions?
Cool. Yeah. So any gel that you're familiar with, basically, other than, I believe, the carbopols or in the pemulins that you might make a gel out of, you can use them with xanthan gum, agarose, gelin, the highly restricted chemical gels that Baglioni's group makes, the Peggy gels and things like that. You can also throw them again into methyl cellulose. You can also put them in a cloth. I've done this with Evalon CR, which is a really nice absorbent textile. I've put a microemulsion into Evalon CR and put that on top of an object and let it sit covered with a polyethylene sheet, and that worked very nicely to initiate dewetting.
Cellulose, chopped cellulose fiber, nanocellulose particles, all those work as well.
They are asking as well, when you prepare a recipe, do you adjust or buffer it?
So anytime we're working on artifacts, except for extremely rare occasions, you should probably be buffering your solutions because you want to control pH and you don't want uncontrolled acid-base reactions occurring on your surface. I always buffer my microemulsions, just like I was showing you in those videos in the modular cleaning program. One thing that I didn't mention there, which is a good thing to mention, is that non-ionic nanostructured fluids that contain polyoxyethylene-based surfactants perform better at around pH 8.5. Anionic surfactants perform far better at higher pHs, around pH 8.5. And we can get into that if you want, but they tend to do a better job at that higher pH.
Oh, sorry. That's probably I think Baglioni systems are just based on distilled water. So I think Luke's taken this to a level of sophistication with buffers and chelators that Professor Baglioni hasn't been doing in his systems. Partly probably because they're more generic, but I think also he feels, well, I shouldn't speak for how he feels, but I think Luke's brought us to another level of sophistication and control of that aqueous phase, where he just uses distilled water across the board.
Yeah, one of the things too about these systems, I don't remember if I mentioned it in the talk or not, but salts also have an effect on the cloud point temperature. So certain salt concentration or ionic content in your solution also decreases the cloud point temperature. So adding a buffer into your solution also will nudge it down slightly. Maybe it's half a degree, 1 degree or something. It's not a big effect, but it has a slightly positive effect. The main takeaway is that it doesn't have a detrimental effect. So you can absolutely put a buffer and chelator in there in the amounts that are generally used in the modular cleaning program, which is at 0.05 molarity. So it's pretty small molar amounts that go into these solutions. And then you can rest easy knowing your system is buffered and it's not going to be having some kind of wild, uncontrolled acid-base reaction on your surface that you're cleaning.
They ask also if you usually rinse your microemulsions, the residues.
Yeah, you always have to do that. And the way I approach rinsing these is the same way I approach rinsing an aqueous solution in a normal aqueous solution in the modular cleaning program. So I use a pH adjusted water. So if my buffer was at pH 8.5, I will clean with a pH 8.5 adjusted water. For the amount of surfactant that I'm using, I don't feel the need to come back with solvent to clear with a solvent because I generally use about 1% surfactant. Chris might have some comments on that, but I generally just use water and I don't have any issues.
I think that's perfectly reasonable. Yeah.
I'm sorry, some questions Carmen has been asking questions and adding things, and sometimes I miss something, sorry. She mentions, I've seen the paper related with EcoSurf series research by Dow, and the diagram phases show that it is necessary a big amount of surfactant for the cloud point changes more in relation to ionic strength.
I don't quite understand what's being asked there. If you're talking about the inverted microemulsion system paper that was published, that's a totally different animal. Those are the water and oil microemulsions.
And those require a lot of surfactant, the Dow research. And like Luke said, we're going to try to come up with better water and oil microemulsion systems, and either the Dow or the EH3 cyclomethicone water systems that Richard kind of formalized.
Mm-hmm. Okay, I see what Carmen's asking here. So it was one kind of a statement about the Dow stuff, and then asking if the cloud point temperature changes in relation to ionic strength. Yes and no. So it changes a little bit when you have sodium ions. It changes a lot if you have other ions in there. Calcium and chloride ions really affect the cloud point temperature of both non-ionic and ionic surfactants. So that's why you should be using distilled water, not tap water, because tap water tends to have a little bit of those in there. So yeah, those can have a dramatic effect on cloud point. Actually, I had my water softener serviced the other day, and that's how they checked to see that I had soft water inside. They were checking the salt content, and they used a surfactant that foamed and phase separated if there was salt in the water. Yeah, it was cool.
There's another question. It says, I'm gonna read it, and I'll try. I was wondering if such small particles of the nanofluids are not about to penetrate the substrates anyhow. If this is something we would aim to during consolidation, it might be something we would avoid during cleaning. This is a question I've always mumbled about regarding the use of microemulsions, and I'm so happy I can ask it now.
I have thoughts on that. Chris, if you have thoughts, you can take it away.
Okay, I think it's a valid point, absolutely. But the thing is, we can put those microemulsions, since they're water thin and water based, we can put them in any carrier that we can put, we can gel water with. So we can do everything from, a methyl cellulose or HPMC or xanthan gum, to things like the PEGI gels, which restrict that, or agarose, which was restrict the movement of that moisture much more so. Certainly, the PEGI gels were developed exactly for carrying microemulsions and removing acryloid varnish from, or paraloid varnish from a Jackson Pollock painting at the Peggy Guggenheim Museum in Florence, or in Venice, sorry. And it was designed for exactly that reason, so that the microemulsion wouldn't soak into the canvas, into the substructure, into the stuff that made the painting.
Okay, and there's, sorry, yes.
Yeah, so that's pretty much what I would agree with, and I would add that if you're working on surfaces that you're worried about that happening with, when you go to clear the surface, a really good way to make sure all of your surfactant is out of there, you can put down that Evolon CR cloth saturated with your clearance fluid, so like the pH 8.5 adjusted water. Let it sit on the surface a bit, let it absorb some of that material up into the Evolon, and then you can repeat that step several times if you would like, and then you can put a dry sheet of the Evolon CR, because it's a very highly absorptive textile, and that just pulls moisture out. So you would have a really good chance of pulling any residue out of the porous structure of whatever you're working on. And when I was cleaning the Egyptian coffin, that's how I approached it when I started working with microemulsions with the matte paint. That's how I made sure that the surface was cleared properly.
There's a last question for the moment saying, what would you use to adjust the pH water for rinsing?
Chris,
That's tested water. So it's a mixture of ammonium hydroxide and acetic acid. The other one that Paolo Cremonesi has been working with is ammonium hydroxide and carbonated water. I think it has to do a lot with your substrate. If you're working with a calciferous substrate, you probably want to go with the carbonated water system. For generally other things, you can get a higher conductivity with the mixture of acetic acid and ammonium hydroxide. But in either case, both the acid and the base evaporate away, as does the water, so there's no residue with these systems.
I had answered that to her before. Good.
I got a private question of someone asking if they should measure the conductivity in a microemulsion solution. That's an interesting question. I don't know how much that would really help you when working on a surface. That's a tough question. I'd probably have to think about that for a bit. My thought would generally be that the conductivity should probably be around what the conductivity would be as a neat aqueous solution. I'm thinking that the surfactant in there might interfere with it with an accurate reading, just due to the way it messes with interfacial tension. I don't know for sure. That's a good question, and I'm not sure how that would interact with, say, a surface that is, like a 300 microsiemens matte painted surface, and then you came at it with a microemulsion solution that was, around 1,000 or 3,000. So I'm not sure. Chris, do you have any ideas?
No, my only observation would be if you have a chelating agent in there, the conductivity will be much, much, much higher. So you could always measure the aqueous phase before you make the microemulsion. I think before you add solvent, you can certainly measure the conductivity of the system with surfactant in it. That'll wet the electrodes nicely, but that's a good thing in that case.
Good. I think it's been good questions so far. Any more questions? You have the opportunity now. misjudgment of the conservation field.
Let's see, someone asked about expelling microemulsions through a needle to reduce the droplet size.
That's for a conventional emulsion. And that works very well for, say, the KSG emulsions that don't have a co-solvent in them, is to squirt it between a narrow needle from one syringe to another, and that'll make a much, much smaller particle size. But that's not necessary for microemulsion because they form spontaneously. So you just mix the ingredients for the microemulsion together and maybe go like that with your little jar, and that's all it takes to make the emulsion, and those default to those nanoparticle sizes.
Yeah, so once you put your solvent into the system with the surfactant, that's the size of the droplet. And so you tune the size of the droplet by how much solvent you put into the system. So if you have a small amount of solvent, the droplets are smaller. If you have a large amount of solvent, the droplets are larger. And that's how you tune the size of those.
And if the system is clear, the droplets are small. So
yeah, it's like I don't think you're really going to get that much more cleaning effect from a 50 nanometer droplet as opposed to a 100 nanometer droplet. If you want to take it to that level, go for it and send me your results. I would love to know what the difference is.
There's another question.
Cool.
Considering that wall paintings usually have high component of salts, especially chlorides, would that component change the cloud point temperature of the microemulsion upon contact?
Great question. So it would. And so that's why there are some surfactants designed for those situations. The amine oxide-based surfactants that I mentioned at the beginning do not change their cloud point temperature when maintained at a neutral pH, so you don't have to worry about that. You could also throw a chelator in there that would deal with some ionic content if you're worried about that as well. But if you were really worried about it, you could use one of those amine oxide-based surfactants plus a chelator in your solution, and then you really wouldn't need to worry about it. What do you think, Chris?
I don't know that it would be such an issue anyway, because Dr. Baglioni's systems were originally used on wall paintings. They were really, I think, initially designed for removing something like B72 or wax from a fresco. And I don't think he's had any big problems. Admittedly, he was using anionic surfactants in the early ones, but I don't think the change in the cloud point is that dramatic, particularly if you have a chelator in there. The conductivity is very high already. So I don't know that the migrating salts would make that big a difference. If it did go up too high, the microemulsion would break, right, Luke?
Yeah, it would phase separate. So if you were using something like the EcoSurf EH6, if you're working on a wall painting, I'm assuming you're in an uncontrolled environment, or there is going to be fluctuations, even if there is environmental control. So I would be a little bit worried just because EcoSurf's cloud point temperature is 40 Celsius. If you're making a swollen micellar solution and that cloud point drops by the 10 degrees Celsius to 30 Celsius, you're pretty close to phase separation at room temperature at that point. So if you were working on something that was had a layer, like a crusted layer of salts on it, then I would be concerned about phase separation. And that's when you would go to your toolkit and pull out that amine oxide based surfactant, and you could use that if you were worried about it. That brings up another really good point, which is that you need to test these before committing to a system. So ideally you would do a very small test, and if your solution phase separated there, then you would know that was going to happen, and you would switch your surfactant out.
Could you switch to EH9? That's got a higher cloud point and very similar structure.
Yeah, I think you could. I think it'd be fine. I'm really hoping that literally within the next couple weeks we'll be able to get some of these other surfactants I've been looking at, and we can kind of maybe even put EcoSurf in the back pocket compared to these other ones I'm looking at. But yeah, I think you could. EH9 would be fine. I don't use Surfonic for these. That's something we didn't talk about. That was in the last Q&A. don't use sulfonic JL80X for developing microemulsions. It's too small of a molecule with, well, it's too small of an aggregation number for that to make quality microemulsions. The way we look at that is that with EcoSurf EH6, it takes about, by volume, a milliliter of EH6 and 100 milliliters of water to get to 10 times CMC. With sulfonic, it takes 3 drops to get to the 10 times CMC. So you could maybe fit 1 drop of solvent inside of that system, maybe 2. So that's really not going to give you a great microemulsion system.
They are asking as well, which are the minimum ingredients you would use to form a microemulsion? So the most basic microemulsion.
The most basic microemulsion that I would form would still have a buffer. I would never use one without a buffer. So I would take my buffer, I would use my EcoSurf EH6, which again is 10 times CMC or 1 weight percent. And then I would put my solvent in for a pure microemulsion, which would be, like 1 milliliter of benzyl alcohol or 1 milliliter of xylenes or 1 milliliter of Gamsol, which is kind of like Shelsol D40. And that's the most basic system with distilled water or purified water of some kind.
And don't forget, this is Luke's adjusted, redone CMC value for the EH6, not the one that's in the current MCP.
Right, and actually, I've been using the MCP's figure for EH6 up until like the last solution that I made, and it's worked perfectly well. The last solution that I made, though, was that Degby system for that basket that I showed you. And that is one where I upped the EcoSurf content, and the cleaning effect was astounding. Like I took the swab and just wiped that soil off the surface, and that was another one of those ones that was thought to be like an insoluble soot layer deposited by a fire. And it was really a kind of a marked improvement in cleaning with the increase of the EH6.
Pure satisfaction. Well, people are saying thank you very much, and that this being a fantastic presentation already. So I think it's because it's 11 in the night here.
Well, I hope it was helpful. I hope that you might try some of these solutions on test pieces. They're really not dangerous to formulate. They're much safer than working with neat solvents or solvent blends. Most of these systems are something like 99% water to 80% water with a little bit of solvent and some surfactant. So if you have a chance, you can try them out for yourself.
If you want to include a chelator in this basic mixture.
Yeah, you can include chelators if you wanted to, sure. Citric acid and EDTA are my go-tos.
Great. Thank you.
I hope that was the answer to the question. Is if the question was just if you can use chelators, yes, you can. So everyone understands the dewetting concept. I hope you all got it because that took me about a full year to understand. That was actually the first question I ever asked Chris. It was during his MCP workshop. I came in and I asked if we were going to talk about dewetting.
And I said no.
No, get out of here.
But it's a powerful, powerful tool, and one that we're, as a profession, just kind of starting to get used to, starting to feel around. And Professor Baglioni has a saying, which I can't remember, about how we have to move from dissolution to dewetting, but he had a different term, a more broad, encompassing term. But rather than thinking about dissolving things to get them off, to have them self-assemble and come off by themselves, use their own physical properties to remove them, rather than just dissolving them and risking washing that material into the substrate.
Mm-hmm. It's really an incredibly complex phenomenon. In our MCP group on Facebook, I have a list of maybe 40 or 50 chemistry lectures, and each one of those consists of something like 30 to 40 lectures, so like 40 hours per. There's one on nanomaterials, and the professor, I think, has 7 or 8 videos that are about an hour long each, digging into the physics and chemistry of dewetting. So if you're interested, you can look at those videos, and you can get a really good understanding of dewetting as a phenomenon, how it works, in pure dewetting examples, which is generally in things like the aircraft manufacturing industry, where they're looking at these coatings and dewetting them at very high temperatures. But you get to understand the physics behind it, and it's very interesting.
There's another question. People ask questions. There are there, I suppose it means, are there other hydrogen bonding acceptor solvents other than the methyl ethyl ketone?
Yeah, absolutely. And you can just do a Google search, and I think there's a whole Wikipedia page about hydrogen bond accepting solvents. There's a lot of them. Here's the thing about dewetting is you actually don't want a solvent that is a really good that is really good at dissolving your substrate, because you don't want to dissolve the substrate. You just want to swell the substrate, solubilize it, and then take pieces away of it from the surface. So MEK and propylene carbonate are more so providing a mechanistic way of removing these, as opposed to a like dissolves like thing going on. So the propylene carbonate and the MEK are basically allowing the micelles to perform a physical interaction. It's not a chemical interaction that's occurring when you're dewetting the film. So the solvent swells the film, which brings the fluid that brings the film below its glass transition temperature at room temperature. So that's what the solvent does. It turns the solid film into a fluid. So once it starts to swell, it's technically a fluid at that point. And then from there, the micellar solution starts to take away little chunks of it and starts to kind of like dig holes into the film. And it's kind of like barreling towards the substrate, because the microemulsion is extremely complex, but the microemulsion is actually attracted to the substrate so strongly that it actually kind of like drills down through that polymer film and starts to create little cavities between the polymer and the substrate. And then more micelles start to go in, kind of like through that same pathway, and then they start to broaden that hole, and then the hole grows, and it forms what's called a shoulder or a hill, and then the polymer rolls in on itself and pulls away from the surface. So I think of it almost like these little hand grenades that are blowing up inside of the polymer film, and that's really what's occurring. So you don't actually need a solvent that would dissolve your film. You need a solvent that's going to enable the micelles to do what they need to do for dewetting.
And I may be wrong about this, but and correct me if I am, Luke, but I think it's the water in the carrier of the microemulsion that is the equivalent of the wax paper. So it's the water that the polymer is pulling up away from, and that's what it doesn't like. That's what it wants to get away from. Is
Yeah.
that right?
Yeah,
Okay.
absolutely. It's the water, but also there is a huge amount of kinetic energy in the micelles themselves at that point. So you have this really strong energetic interaction between the surface and the micelle that also creates a charge that pushes the polymer away. So you have the water doing that, because your film is generally hydrophobic. Your film is generally, nonpolar itself when we're talking about these, coatings like B72. So you have a very highly polar solvent like water that it doesn't want to be in contact with. And exactly like what Chris said, it wants to pull away from it. We talked about that water droplet. The lowest energetic cost is for that droplet to be a droplet, so that it's not in contact with something that it doesn't have the same surface energy. So the film rolls away into itself, so that it doesn't have as high of an energy cost to exist, basically. And so it's rolling away from the water, if that makes sense. It's basically the reverse situation of a water droplet on a waxed surface, if that makes sense. So now it's like you're pulling the wax away, and it's like rolling in on itself to get away from the water, because you have a very big difference in surface tension and surface energy.
Someone asked about our Baglioni system's proprietary or secret. He kind of hints at some of the recipes in the journal articles, like in Langmuir, that sort of thing. I don't think he really gives recipes away in the conservation literature. My understanding is this has to do with the EU funding he got, and it was a grant to kind of establish almost a business model. So until the 5 years are up or something, he can't, this is my understanding, he can't really give out the recipes as such.
I've asked, he's not going to do it.
Right. Oh, ever? Okay.
Well, I mean, maybe at some point. He's not giving them to me.
Okay.
What I've been basically doing the last year is redesigning his systems. So I'm basically bootlegging his systems. That's what I presented to you today. It's a deconstructed Baglioni system, and I've gone through and through his papers and other things, reconstructed kind of like what surfactants he was using and how he was doing this. And so at the beginning, I showed you one surfactant, which is the one I'm pretty sure he was using. And so once you have that variable, then all the other variables fall into place, which is just the water and the solvents, which he's published, about a lot. So once you have the right surfactant, then you're kind of ready to go.
And then Luke's augmented that by adding chelator and controlling the pH. Controlling the pH seems like a really critical improvement to Baglioni's system, nascent system.
Mm-hmm. Yeah, especially if you're going to work with anionic surfactants, you have to keep the pH stable and elevated at about 8.5. Because remember, if it's anionic, you have a negative oxygen on there, unlike sodium lauryl sulfate. And if you have a low pH, let's say 5.5, you're going to start protonating that surfactant. So you're going to start, that oxygen is going to start grabbing hydrogens from that, slightly acidic solution, and that reduces the efficacy of the system. So you need to keep it buffered and stable.
And they add, is it also related with the surface tension of water?
Everything is surface tension. Another way of looking at surface tension is interfacial tension, which is why, I made a big deal about it on that one slide. There's solid-solid interfaces, there's solid-liquid interfaces, there are liquid-liquid interfaces, which were mainly conservative, but there's also the liquid, atmosphere interface. So that's another interface. So it's about interfacial tension. And surfactants are really good at decreasing interfacial tension between different phases. I mentioned the entropy of mixing earlier. The entropy of mixing relates to the relative value of energy within different solvent phases. Generally, that energy difference is about 50 millinewtons per meter. And so what surfactants do is they bring down that difference in energy from 50 to 1 or 10 millinewtons difference. And that's really the thing. So surface tension, surface energy, and interfacial tension, interfacial energy are all related. It's kind of like 4 different ways to say the same thing.
And you can throw in solubility parameters too.
Now that's a can of worms that I think my brain would melt at this point trying to get into that.
Right. Well, that also is a direct relationship to the surface energy. And
she wants to know if this surface tension is related in the dewetting process.
As far as just purely in the solution, because that's the entire thing is predicated on the interfacial tension being lowered between the phases, because what that does is it reduces energy costs of the different phases in the system. So if you're used to looking at energy diagrams, what it basically does is it lowers the energy cost for that film to go from a flat solid film to a balled up dewetted film. So it goes from a metastable state to a thermodynamically stable state. So the metastable state is up here. The thermodynamically stable state is down here. Normally it has to climb a big energy hill. It has a big energy cost. That's the activation energy. When you have the surfactant, it just has a little bump. It has to go through the hill. The size of the hill decreases. So you have less energy for it to slip down and then start going down that hill into the thermodynamically stable equilibrium position. So that's what the surfactant is doing. You're lowering energy and energy costs. And then the polymer film itself provides the energy to de-wet itself. It's actually really cool.
This may confuse things, and I may be wrong, but Luke just talked about that high energy hill between the film that's been spread out versus the film that turns itself into a ball. Think about what happens in a fire with a coating. What does it do? It beads up. So we've added that energy from heat from the fire and beaded up that varnish layer, whatever, if you've seen a painting that's been on a fire. And it's melted and gone to that spherical state, or trying to go to that spherical state.
I love that. I'm stealing that and putting that in every lecture on this from now on. That's a great way of looking at this. Absolutely. So what the fire has done is put a ton of thermal energy into the system, and that enabled the de-wetting. What we're doing is just making it so that there's so little energy required that the quantum, so you get into the quantum vibrations and how waves move and oscillate. That tiny bit of energy is what gives it the energy to just go like over. It's like a speed bump. It just goes boop, and then now it goes down that hill into the thermodynamically stable position. So it just we're shrinking that hill size so much that the energy of the film itself de-wets itself, and then it goes into the thermodynamically stable position. And that's all related to interfacial tension, surface tension, interfacial energy costs. That's all related in there. And the surfactants, like I showed in that one slide, can bring down the surface energy to like 0.00001 millinewtons per meter, which is extremely low. So that's how this works. It makes the energy cost very small.
I have Corinne asking, does the hydrogen bonding acceptor solvent in the emulsion have to be water soluble?
Yes, it has to be water soluble to a particular extent. A little over 20 grams per 100 milliliters needs to be soluble. That's right. If you look it up on Wikipedia, that I'm giving you that measurement because that's how you'll find it generally. So it's at least 20 grams per 100 milliliters is required for these solvents that have a similar polarity to MEK and propylene carbonate. So yeah, they definitely need to be water soluble to some degree. They can't be water miscible, right? So if it's water miscible, then it can totally, it can be in any proportion with water, and that's not going to provide the interaction necessary to strain the micelles.
So you can't use acetone instead of MEK.
That's what I was going to, but for some reason, everyone was really insistent on acetone the other day. But and I think you mentioned that you couldn't do it because it's water miscible.
Yeah.
And I was trying to explain it molecularly, which and go into the different charges in the MEK, the dipole moment, and explain it from that perspective. But yeah, that's why you can't use acetone. There's really no interaction there.
Yeah, and I have a lot of comments saying thank you for recording these sessions because they want to revisit and they want to sometimes think in new concepts, and they are asking, where do you put them in the Facebook modular cleaning programming practice page? Where are they to find them?
Oh, well, so we just have been posting them just on the regular feed timeline. And I think if you just click on videos on the page, it shows you like all the, I think if you click media and then you click videos, then it shows you all the videos that have been posted. And there are a lot of other videos in there as well, showing you how to mix solutions and, all kinds of stuff.
I recommended to use the find the magnifier button that is always at the top of the page to try to find the videos. But I also, every month, when I send the emails to inform about the sessions. I do send them the links. I needed to make them aware that they won't be indefinitely available, isn't it?
We've changed our mind on that. They will be indefinitely available.
Okay.
Unless the speaker decides they don't want it to be. We will certainly, we got a lot of complaints about that.
I thought I was getting very lucky because you said they'll be available for a month after the session, and I was still able to see some of them, and I was like, oh my gosh, I'm not saying anything just in case.
Well, it's kind of like one of those things where someone didn't really care about something until you were going to take it away. All of a sudden, everyone really wanted the videos when we mentioned it was only going to be up for a couple months or something like that. We really don't have any problem. It was really more so of, we're going to have a lot of guest speakers. And so, a lot of this is their, intellectual property. It's their material. And so we wanted to put limits on that and wanted to introduce that early on. But people got a little upset, but it is still going to be up to the discretion of whoever a guest lecturer is. Or if someone decides they want this material to come down, then it'll come down. But that's really it.
Okay, I can wipe my tears now. I'm happy now.
Well, thank you all for coming. This was a really fun Q&A session. It's the only time I get to talk about microemulsions this in depth. So these were great questions. I had a lot of fun answering them. This video will be put up as a separate video from the original lecture, but Jenny will get that link and you'll be able to access this later on.
Thank you. Thank you very much for doing this for us.
Thank you very much.
Thank you all for your attention and for asking.
Yeah, thank you all.
Great questions.
For coming.
Thank you.
Thanks, everyone. Good night.
Okay.
Thank you very, very much. It really was fantastic. Thank you.
Yeah, you're welcome.
Me too.
Bye-bye.
Bye.
Bye. Thank you. Bye.
Bye-bye.